Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at rational and irrational numbers. So we're going to start off by talking though about real numbers. So real numbers are just the numbers you know. At this point, the only numbers you know are real numbers. So 3.3 recurring, pi, 7, minus 265, all of them are real numbers. The real numbers are made up of two disjoint sets, the rationals and the irrationals. So every real number is either rational or irrational, but it is never both. You can't have a number that's both. So we use this weird R to denote real numbers, and the subset of rational numbers is this weird Q. This here just says Q not, means not rational. So which kind of numbers go in each? So rational numbers include all fractions in the integers. That means they have an integer numerator and an integer denominator. So something like 3/5 is a rational number. All terminating decimals like 0.23 are rational. All recurring decimals like 1.4 recurring, they are rational. There is a subset of rational numbers, we denote it Z, that is the integers, whole numbers. So integers can be positive or negative. So -4 is an integer, 0 is an integer. And there's another subset of integers. This group is denoted N for natural numbers. That includes just the positive integers. So 1, 2, 3, 4, 5, 6, all that, they're all natural numbers, which means they're also integers, which means they're also rational. So natural numbers are a subset of integers. Every natural number is an integer, but not every integer is a natural number. So negative numbers like -4, they are integers, but not natural numbers. Similarly, all integers are rational, but not all rational numbers are integers. So if this includes all terminating decimals or recurring decimals or fractions in the integers, all integers, positive and negative, which numbers go here? So because this includes all terminating and recurring decimals, in here will be numbers whose decimal expansion is neither terminating nor recurring. So examples of this are numbers like √2. If you put the square root of 2 in your calculator, it's like 1.4142 blah blah blah. Its decimal goes on forever, but there is no pattern to it. So for irrational numbers, it turns out if you square a non-perfect square, it will always be irrational. So 10 is not a perfect square, so the square root of 10 is irrational. If you were to put this on the calculator, you get a decimal that goes on forever, but for which there is no pattern. So just in case you've forgotten perfect squares, so perfect squares are numbers that can be written as something times by itself. So 0 squared 0 is a perfect square, 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on. These are the perfect squares. If you square root a perfect square, you get an integer. So something like the square root of 9 is actually 3, so it's a natural number. But if you square root any number not on this list, it will be irrational. So 15 is not a perfect square, so square root of 15 must be irrational. So we've also got numbers in there like pi, the ratio of a circle's circumference to its diameter. So pi is 3.14159. It goes on forever, but there is no pattern to it. So what about something like pi plus 1? Well, if I do pi plus 1, it's only going to change this part of the number from a 3 to a 4. It's going to be 4.141592653, blah, blah, blah. So this decimal goes on forever and there is no pattern. So this decimal goes on forever and there is no pattern. So something like pi plus 1 is also irrational. It turns out if you add a rational number to an irrational number, like √2 plus 2, that number is irrational. It's going to have the same decimal expansion as √2. We knew that √2's decimal goes forever without a pattern. So this number will have a decimal expansion that goes forever with no pattern, and therefore it's irrational. Whenever you add two rationals together, you always get another rational. So for example, if you add 1 over 4, which is rational, to 0.2, you get 0.45 or 9 over 20. So we say that rationals are closed under addition. If you add any two rationals, you get another rational number. If you add two irrationals, however, sometimes you get a rational answer, sometimes irrational. So if I add pi and minus pi, these are two irrational numbers. Pi is this number, minus pi would just be negative 3.14159. So here we have irrational plus irrational. This would actually equal 0, which is rational. So if you add together two irrationals, sometimes you get a rational answer, sometimes you don't. Something like root 2 plus root 3, that is still irrational. So it can be hard to determine, but when you add two rationals, the answer is rational. When you add a rational and an irrational, the answer is irrational. When you add, however, two irrationals, sometimes you get a rational answer, sometimes you don't. Now, just to let you know, we use this symbol to indicate group membership, something that's in a set. So, for example, 3 over 5, this says is in Q, the rational numbers. This is how we write mathematically 3 over 5 is a rational number. If I wanted to write pi is not a rational number, I'd write pi is in the set of irrational numbers. This means not. Pi is irrational, 3 over 5 is rational. All right, let's now look at solving a few problems. So let's try this one first. Find an irrational number between 2 and 3. So we know that 2 is equal to the square root of 4 and 3 is equal to the square root of 9. 4 and 9 are perfect squares. We also know if we square root a non-perfect square between 4 and 9, it will be irrational, more than 2, less than 3. So all we need to do is pick a number like root 5, root 6, root 7, whatever. This is irrational because 5 is not a perfect square. This is irrational because 6 is not a perfect square. Because 5 and 6 are between 4 and 9, their square roots are between 2 and 3. So the square root of 5 is about 2.236. It's more than 2, less than 3, it's irrational. Let's look at this one. Show that the square of a rational number is rational. You see, all rational numbers can be written as fractions in the integers. So I'm going to use a over b to represent a rational number where a and b are integers. So any rational number can be written as a fraction in the integers. Any number that can be written as a fraction in the integers is rational. So this just represents some random, some arbitrary rational number. It can be literally any rational number. Now, if I square this, we know from our index laws, we just square the top and square the bottom. The idea here is a squared will be an integer. If a is an integer, a squared is an integer. Similarly, if b is an integer, b squared will be. So if you square a rational number, you get another rational number. This is rational because it must be an integer on top and an integer on the bottom. That proves that if you square a rational number, the answer is rational. It's not actually the case for irrational numbers. If you square root 2, for example, you just get 2. So sometimes if you square an irrational number, the answer is rational. If you square pi, that's still irrational. So if you square a rational, the answer is rational. If you square an irrational, sometimes rational, sometimes irrational. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.